In your lecture notes, you have noticed that there are some pages which talks about some hints on how to draw these diagrams and a methodology to draw it. The best way of this is to see it in practice, so I strongly suggest that you go through them, and when you look at the tutorials you will understand why this is happening and how we're applying it. So let's start with the examples. The first example is a simply supported beam. So there is a pin here and there is a roller here. This is a simply supported beam. It's uniformly distributed load. So W is distributed uniformly from here all the way to here, so I can replicate and replace this uniformly distributed load with a single concentrated load, which will be whatever W is times the length. Let's consider that the length of this beam for now is L. It can be 5 meter, 1 meter, any dimension that you want. Let's bring the load as well. So this concentrated load, which will be an equivalent to this uniformly load, as we discussed, will be W times L. This will be the equivalent concentrated load, which actually is representing this distributed load. On the other side, because I have two supports, I quickly draw the support reactions as well. Let's say this is point A, this is point B. This will be RB, and this will be RAY, and then this will be RAX. Similar to always. If I have drawn it a little bit this side, I mean this is underneath this pin, so don't worry. The reason that we're doing this is to find and figure out what is the bending moment diagram and what is the shear force diagram for this beam under this certain loading condition, which will be the external loading, as well as this certain support condition, which will be a simply supported beam. The first step, similar to whatever we have done so far, is to figure out what are the reactions. So let's calculate the reactions. And I'm sure that all of you by now know how to calculate the reactions using the three equations of equilibrium. So summation of all forces in x equals to 0, this direction positive, and this gives me RAX equals to 0. As you can see, there is no other force in x direction, so it's only this guy. So RAX equals to 0. That helps me a little bit. Summation of all forces in y direction equals to 0, and I consider this direction as positive. That concludes that this guy plus this guy equals to this equivalent force. So RAY plus RB equals to WL. These guys are positive going upward, WL was negative, so instead of putting it minus WL, I put it on the other side of the equation. We said after a while we speed up the process. Now you can argue that the entire thing is symmetric, so probably RAY and RB are equal to each other and they're half of WL. Each of them carries half of the reaction to this load on top of it. But if you don't trust that calculation, let's do summation of moment along any point with this direction as positive to see whether we are right or not. We said whenever we want to do the moment, we take it along a point which I get rid of most of the unknowns. So most of the unknowns are in point A, so let's get it along point A. Moving from here, RAY and RAX are zero distance to A, so they won't generate any moment, because if you remember, moment was force times its perpendicular distance. WL has a perpendicular distance to the pin, the point A that I have, and it's, if you again remember, whenever we had a uniformly load distributed which is rectangular, that concentrated equivalent load is applied at half of the length. So this point is actually L divided by 2. Isn't this a force with a perpendicular distance to a point? So if I follow the arrow of WL and I go with the center of A, as you can see, it goes something similar to this. Isn't that the same direction that I have considered positive here? Yes. So it will be that force, which will be WL, times the distance from here to this point, which will be L divided by 2. And it's positive because it's in clockwise direction. But look at RB. RB has a perpendicular distance all the way to point A. And if I follow the arrow of RB along point A, as you can see, is counterclockwise. So it will be negative. I'm just writing it underneath it. RBY times the distance, which is L, equals to 0. The entire of this equation equals to 0. From this, if you see WL to the power of 2 divided by 2, if I take RBY to the other side, RBY will be equal to whatever this is divided by L. So it will be WL divided by 2. I just simply solve that equation. And if RBY or RB, let's call it RBY so it's not confusing. RBY. If RBY plus RAY is WL and RBY is WL divided by 2, so definitely RAY is the other half, which we actually guessed it in the beginning that between these two, this load is going to be distributed. Half of it for this, half of it for this. If that load is WL, half of it will be for this, half of it will be for this. So you can either follow the right way and calculate it, or you can say it's symmetric and I can see that is half of it. Now, the methodology to figure out the bending moment and the shear moment diagram indicates that you start from the left side of the beam. You carry on until something changes. That something changes will be an external concentrated load applied, an external distributed load just starting, a moment applied, or a pin or a support suddenly appearing. So if I start from here, I'm starting from the distributed load. So nothing is changing actually. Everything is constant until I reach to this point that I have the equivalent concentrated load. Whenever you reach to that point, you get a section. You cut it. Let's say I cut it here. As we carry on with other examples, you will understand when and why I'm cutting. Let's assume that I'm cutting it here. So a little bit before, a tiny bit before L divided by 2. So if I take that section out, let's divide this reactions and I'm going to write it here. If I take that section out and I zoom in, it will be something similar to this. I have an A, which will be this point A. I have a distributed load on top of it, which will be W. I have a reaction over here, which is RAY, and I just calculated it. RAY is WL divided by 2. So I just replace it, WL divided by 2. What else do I have? I have to give a length here. So the length, I'm saying that I'm cutting it a tiny bit before L divided by 2. I call it X. The entire length of this, I call it X. It's just a name. I want to call it X. Why not? And then do you accept that if this is a uniformly distributed load, this can be represented by a concentrated load which is just for this area, and I can represent that with Wx. And where is it applied? Is in the middle of x, because it's a rectangular load. So it will be x divided by 2 and x divided by 2. My new length is x. I'm cutting it before L divided by 2. At this point, there will be a shear and there will be a moment. What I do, I draw the positive signs of shear and the positive signs of the moment, which was in the lecture notes as well. If you remember these, you see I'm cutting it from this side, so I'm looking at this side, so I'm drawing the positive one of this and the positive one of the moment. So positive sign of shear will be something like this, and shear is a function of x, as we just discussed in the lectures, as well as I'll draw a moment which will be something like this, and that moment will be a function of x as well. So at this point, which will be x, I will have a shear and a moment. And the direction that I draw them is, because I'm cutting the right side, I just draw the positive ones. This is the positive sign of shear on the right side, and this is the positive sign of the moment on the right side. So Vx is the shear function, and mx is the moment function. And you all know that any graph that we draw actually is drawn by a function. So if I can calculate what is this shear function and what is this moment function, I give different values of x, which can be, if this is my whole length is L, if this is like 0.1 L, 0.2 L, 0.3 L, I can put it in these functions and I can carry on what is the shear, what is the moment, and I can draw it. How can I calculate what is this V and what is this M? Didn't we say that my entire section is in equilibrium? So we use the same formulation that we always had. Summation of all forces in X, summation of all forces in Y, and summation of the moments. Let's see whether it works or not. Is there any X? There is no X, so I'll forget about it. Let's do summation of all forces in Y direction. Let's bring this up a little bit so we can see. Summation of all forces in Y equals to 0. Let's assume this direction as positive. I have an RAY, which I can later replace it. I have the concentrated equivalent load, which is coming downward, so it's negative, Wx. And I have this function, Vx, which is coming negative as well, is coming downward. So I put it minus Vx equals to 0. I sort this formulation for Vx, because Vx is my shear function. So what happens? First of all, I can replace this with WL divided by 2 because I already have calculated it. I bring Vx to the other side, so Vx will be equal to WL divided by 2 minus Wx. Just put this to the other side, this. Now, this is a function of x. So if I give values for x, it should give me values for the shear. Exactly like a function like this. If I give a value for x2, my y will be 4. Let's give it some values. If x equals to 0, my v of x equals to 0 will be equal to WL divided by 2. I'm just simply putting 0 instead of any x in this function. If x equals to L, yes, because nothing is happening in my beam, the entire beam is the same thing, so probably the function of shear everywhere over here will be the same thing. So that's why I'm putting L in it as well. Let's see what happens. If I put x equals to L, my v of x equals to L will be equal to, I'm putting L here, L, WL divided by 2 minus WL. What will leave? Only a half of L, but negative. WL divided by 2. Simple maths. If I want to see what is the shear in the midspan, I'll put x equal to L divided by 2. My entire length of the beam was L. I'm just putting the midspan because I can guess that if this is my beam and I'm putting a distributed load in it, it will zoop, go like this, a happy face. And there's a high chance that my maximum deflection is in the middle, as well as wherever my maximum deflection is, my maximum internal bending moment will be there as well. That's why I'm not only getting the x equals to 0 and x equals to L, I'm getting, the shear in the middle as well. So let's see. Sorry, what did I write? X equals to L2. What will it be? I'm putting L2 here. WL2 minus WL2 will be 0. So it's saying that the shear in the midspan will be 0. And I mentioned that I'm putting L divided by 2 because I'm interested in the moment in that point as well. So if I draw the moment diagram, I will see what will be happening in that point. But now just considering the beam, I have calculated what is the shear here at x equals to 0. I have calculated what is the shear here at x equals to L, and I have calculated what will be the shear at x equal to L divided by 2, which means the midspan. Let me draw the shear function. So I will have this figure, and I'm just writing the summation of all moments equals to 0 with this direction as positive. I need a point, as always, to take the moment along. I said we always take the moment along the point that I have the maximum unknowns. Compared to point A, which I know this is the force, this is the point which I have the maximum unknowns. So if I put, let's say, call it Z, and I take a moment along point Z, you can call it O, doesn't matter. I'm actually getting rid of this Vx. Because Vx times, like moment is force times distance. Vx doesn't have any distance to that point. Let's see what happens. I have this WL, and if I follow the arrow along point Z, it will be a clockwise. So it will be a positive WL divided by 2 times its distance. What is the distance? In this case is x. So times x. Then I carry on to the concentrated load. The concentrated load, if I follow the arrow with the center of that point that I'm getting the moment, you can see it goes counterclockwise. So it will be negative whatever the concentrated force is, which is Wx. Remember, this W is the uniformly distributed load. Wx is the equivalent concentrated load, which was that W times the length. And what is the length from here to here? The perpendicular distance is x divided by 2 times x divided by 2. Because that concentrated load, because it's rectangle, will be applied in its middle. This equals to, am I done? No, we have a moment here as well. So I have to consider this moment as well, although it doesn't have any distance, but it's a moment itself. So this is not finished yet. Is it positive moment or negative moment? Is it following my direction? No, it's counterclockwise. So minus mx. Now it's finished. Similar to the shear as well, I brought the Vx in. This is my moment function. Let's make it a bit nicer. So I'll bring mx to the other side. Mx equals to WLx divided by 2 minus Wx to the power of 2 divided by 2. this and this. This was my shear function. This is my moment function. And similar to this one that I put different x values, I'll put it here as well. If my x is equal to 0, meaning the beginning of the beam, if this is 0 and this is 0, my m of x will be 0. So I just simply put 0 instead of the x's. If my x is equal to L, meaning the end of the beam, L times L to the power of 2, L to the power of 2. Again, my mx will be 0. Simple maths. Now, we were saying that, okay, I'm bending this, and I can guess that the bending moment in the middle is important, and it will be a big number. So let's give the same x equal to L divided by 2, which we did for the shear as well. What happens if I put L divided by 2 here and here? If you calculate it, mx will be w L to the power of 2, excuse me, divided by 2 of that coming down, divided by 8. Yes, so this will be the midspan. And this was the midspan. Now, can't I draw this? I have different location of my beam, and I have the values of the shear force as well as the moment force, bending moment. Let's see whether we can draw it. Let's bring the beam out. I'll zoom out. Let's bring the beam out again. So I have this beam, length of L. I have the pin here and the roller here. I have a distributed load on top of it. This can be, for example, the wind distributed on top of a roof, W. As I mentioned, we do some dashed lines to follow exactly the length of that beam. Let's say one of them will be for the shear and one of them will be for the moment. So this for the moment and this for the shear. This will be the shear diagram. This will be, oopsie, this will be the moment diagram. If its shear is V of x and the unit, for example, is in kilonewtons or newtons, if its moment, it will be m of x and the unit will be kilonewtons times the unit of length. What is this? This was the length, or let's call it x, and let's say the units are in terms of meter. In this example, we don't have the units, so it's like just unitless, but I'm just preparing you for the coming ones. Now, simply I just read it. So it says shear at x equal to 0 is WL divided by 2, and it's positive. So WL divided by 2. It says find the midspan. So probably this is the midspan. So let's say this is L divided by 2 if the whole thing is L. It says at the midspan, the shear is 0. At x equals to L, which will be the end of the beam, the shear is negative WL divided by 2. So negative WL divided by 2. It's a simple diagram, so dot 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 is here. Now, do you remember we had these formulations of d of v by d of x is equal to wx, and d of m to the d of x is equal to v of x. So always the shear was a higher order than the applied load, and the moment was a higher order than the shear load. My load over here is what? It's a constant load. So if this is constant, this should be linear. That's why that if I want to connect these points, I draw a linear curve. And the shear is the area, the shear diagram is the area underneath the curve with the length axis. Anything above will be positive, above the length axis will be positive for shear. Anything below will be negative. Well done. You have calculated your first diagram. Now, looking at this, from here to here, it's about WL. If I look at this, isn't that I went up equal to RAY, which was W divided by 2. Then I followed and I suddenly came down all the way equal to that massive sword, WL. And then when I reached to the point, the end point, I went up again equal to my last sword. Do you remember the samurai sword? A little bit of sword, a massive sword, a little bit of sword. And because this is distributed, the line will not go constant, it will go like this. In the previous examples, there wasn't any distributed load, so there wasn't any load, so the loading was 0. That's why the shear was constant. Let's look at the moment diagram. Again, I have calculated all of them. It says if x is equal to 0, moment is 0. So at x equals to 0, if x is along the length of the beam, my moment is 0. It says if x equals to L, the moment is 0 again. So at the end of the beam as well, my moment is 0. I can't draw such thing. There is something happening in the midspan as well. So it says at the midspan, when L is equal, x is equal half of L, your M is WL to the power of 2 divided by 8. We said for moment, it's easier to consider positivity as downward because you are writing it for the tension side. We will discuss it in a second. So let's say positive omega L to the power of 2 divided by 8. So at L equals L divided by 2, my moment is over there. Now, how do I know whether this is straight line or cubic line or parabolic line? I get help of this. Didn't we say that the moment is a higher order than the shear? So if my shear is linear, my moment will be parabolic. So instead of writing like a straight line, I go parabolic. And this will be my moment diagram. Why did I put positive? Because I said whatever is down, we put it as positive. Why is it positive? Because under such loading, my beam will go whoop. And then that, if I put two eyes here, if you look at it, it's a happy face. Happy face, sagging, drawing it for the tension side. All of these are now coming in to indicate that this is a positive diagram. Using these two very important equations that we solved together as well, and we proposed them together as well, we concluded that if the load is constant, the shear will be linear. If the shear is linear, the moment will be parabolic. Another assumption was, if it's under distributed load, where was the maximum moment? Probably in its middle, where the maximum deflection happens. So over here is maximum moment, and probably the maximum deflection of the beam, which we will learn how to calculate it later on. Isn't this the maximum deflection? Yep. Where is it? In the midspan.